All right, problem 18 is a perennially vexing one for this segment of the material. It's actually, the part B anyway, is a clever iteration of the Prisoner's Dilemma game, but let's get there in due time. First off, notice that the price of each pail, $6, constant. You probably have different numbers, but it's the same methodology. Notice that the marginal cost of carrying the one is 4, and the marginal cost of carrying that second one is 5. And so if Jack and Jill must decide whether to carry 1 or 2 pails of water, how many pails will each child choose to carry? Well, they'll each carry 2, because they get $6 for carrying it down. 6 is greater than 4, so they'll bring the first one down. Will they bring the second one down? Yes, 6 is greater than 5. It gets interesting when they have to split the revenues, and this is what creates the game, because now they get only half of what they earn by carrying the water themselves, and half of what the other one earned. So let's just fill out the game matrix. Notice that if they each carry down 1 pail, there's a total of 2 pails at $6 each, $12 total. So they're divide that in half, each gets 6, and each has spent $4 of effort bringing them down. So they end up netting out 2 each. Now let's think about the case where Jill carries 2 pails down and Jack just carries 1. So here, the benefit of, they'll have 3 pails total down the hill. That's $18. They split it, so $9 of revenues each. Jack has carried 1 pail down, so he's spent $4 in effort, so his net is 5. His net benefit is 5. Jill has carried 2 down. She spent $4 worth of effort for the first one, $5 for the second one. That's a total of 9. 9 minus 9 is 0. Now it's a symmetric game, so if Jack is the one carrying the 2 pails, as he would be in this square, Jack would have 0, and Jill would have 5. And then finally, if they each carried 2 pails down, they'd have 4 pails total, $24 total, times divided by 2, so that's $12 each. They would have each spent 4 bringing the first one down, 5 bringing the second one down, total of 9, so their net would be $3 each. But let's think about how this game is going to work out. So notice, let's just take it from Jill's point of view. If Jack carries 1 pail down, Jill's going to think, do I carry 1 pail or 2 pail? And notice that she'd get 0 if she carried 2, and 2 if she just carries 1. So Jill's only going to carry 1 if she thinks Jack is going to carry 1 pail. Well, what's she going to do if she thinks Jack is going to carry 2 pails down? Well, notice she could carry 1 pail and make 5, or she could carry 2 pails and make 3. So again, she's just going to carry 1 pail. It's a symmetric game, so Jack also has a dominant strategy. No matter what Jack does, Jill's best play is to carry 1 pail down. No matter what Jill does, Jack's best play is to carry 1 down. So we know from our work with Prisoner's Dilemma in class and in our reading that the outcome is going to be they each carry 1 pail of water. So notice that this is an inefficiency, because the best outcome for both of them, the mutually best outcome, is where they each earn 3 for a total of 6. At the Nash equilibrium, they're only earning a total of 4. So this is that classic Prisoner's Dilemma case. Notice that each has a dominant strategy, and that when each plays their dominant strategy, they end up at a Nash equilibrium that's not the best they could do. If they could cooperate, make a binding agreement to each carry 2, they'd both be better off.